Newton's second law of motion says that the net force, or all of the forces acting on an object, is equal to the mass of the object times the acceleration of the object in that direction. So to show everybody how to solve these types of problems, I have a very simple problem that we're going to go through step by step. A 10-kilogram wagon is pulled with a force of 30 newtons. The wagon accelerates at 2 meters per second squared. What is the force of friction acting on the wagon? So, first thing you want to do is draw yourself a little dot to represent your object. So here we go, a little dot to represent my wagon. Then I want to think about the velocity and the acceleration. This problem does not say whether my wagon is moving left, right, north, south, east, west, up, down, whatever. However, we are just going to pick a direction. I'm going to go ahead and say that my wagon's being pulled in that direction. So that's the direction of my velocity. We're never going to use the velocity in the equation, but identifying the direction of the motion will help us identify which direction should be positive, which direction should be negative, and then also decide is our acceleration positive or negative, and even helps us figure out which direction the net force is in. So if I choose my velocity to the right, I know that my wagon is accelerating at 2 meters per second squared. I can assume that that means that it is speeding up. So if it's speeding up, my acceleration and my velocity are in the same direction. They're working together. I also am going to pick my positive and negative direction. So step 1 is going to be to choose positive and negative directions. So to do that, we're going to define the positive and negative direction by just creating ourselves a little coordinate system over here. So if my velocity is to the right this way, that means that the direction of my motion is positive. So I'm going to make to the right positive, meaning the left is negative. Because I don't have any motion up or down, it doesn't matter which one you choose to be positive or negative. I'm going to make up positive and down negative. So now I've chosen my positive and negative directions. So next up on my list is to draw a free body diagram to scale. So again, in order to draw it to scale, we have to know which direction the net force is in. If my acceleration is to the right, that means that my net force is also to the right, meaning that the forces going to the right have to also be larger than the forces going to the left. So in this case, we've got a pulling force to the right. So I'm going to draw my force vector, and I'm going to label it FA for applied force. I also know that there's friction, and friction always opposes the motion. So if my wagon is moving to the right, that means friction must be going to the left. I'm also going to make that vector significantly smaller than my applied force, because again, I know that the acceleration is to the right, meaning the net force is to the right, which tells me that the forces on the right side are larger than the forces on the left side. I also know that there is a normal force up because, again, my wagon is on a surface, it's on the ground, and of course we've got gravity acting. Instead of writing FG, I'm going to simplify and just write MG, skip a step later on. If you'll notice, I made my normal force the same length as my gravity because they are balanced, so I needed to show that by the size that I drew them. So now I've got my free body diagram drawn to scale. After I do that, I am going to write myself an XY force table. And the reason we write a table for the X and Y forces is so that we don't get anything confused, so that we keep everything neat, and it makes writing our equations a lot easier later on. So my X and my Y table. All I'm going to do is use my free body diagram and say, okay, in my Y direction, which is up and down, I've got Fn and I've got Mg. So they're going to go over here in the Y side of my table. So I'm going to list Fn and Mg. It's that simple, nothing difficult here. Then I'm going to do the same thing, but in my x direction. So I've got the applied force and I've got the force of friction. So they are also going to go in my table. The applied force and my force of friction. That's it for that step. I'm just going to leave that how it is for right now. And then I'm going to think about the signs. Remember, force is a vector, so we have to have positive and negative to show the direction of those forces. So we are going to use the help minus hinder method. And to use that method, you just can think to yourself, is this force helping the motion or is it hindering the motion? Helping motion, those are going to be positive forces, and they assist the motion, or in other words, they go in the same direction. Oh, not more. And then my hindering forces are negative, and they oppose the motion. So basically, your helping forces help the object move. If it's a hindering force, it's going to hinder that motion. It's going to work against the motion. So you can think of help minus hinder. You can also take a look at your coordinate system that you drew up here, and that will help you as well. So the applied force, if I look over here, then at my applied force, that is to the right, and to the right is positive. I also know that the applied force is the thing that is causing this motion, so it's definitely helping the motion. It's going to be positive. Then I'm going to look at my other force, my friction force, which is in the opposite direction of the motion, so that is negative. It is hindering that motion. Friction will always be negative. Every single problem, friction is negative. There's never a time where it will be positive. Because we don't have any motion in the y direction, you just are going to rely on the x and y signs that we've already drawn. So for the x direction, Fn is up, so it's going to be positive. Mg is down, so it's going to be negative. Pretty simple. Decide the positives and negatives. Then our fifth step is going to be to write the x and y F equals ma equations. And this is really very simple. But remember, when we break things down into x and y dimensions, the x's never go with the y's. They are always separate. So we are going to have a net force in the x direction equal to the mass of the object times the acceleration in the x direction. And we are also going to have a net force in the y direction equal to the mass of the object times the acceleration in the y direction. So it's super important to distinguish between the x's and the y's. That's where our table comes in. Net force just means adding up all the forces. So for my x direction, I'm going to take a look at my table here and see those are my x forces. So F A, and again, I'm just adding them, plus I've got a negative F is equal to the mass of my object times the acceleration in the x direction. Pretty simple. I'm going to do the same thing for my y direction. Here are my two y forces, so that's going to be Fn plus my negative mg is equal to the mass times the acceleration in the y direction. So there I have my x equation for my sum of the forces and my y equation. From there, it's pretty straightforward. You're going to plug in what you know, and then you're going to solve. So this problem is asking me to solve for the force of friction. So if I want the force of friction, that only applies in this equation. So realistically, I don't even need this y equation, but it is always good to write it out because we are going to do a lot of problems where you will need both equations. So it is a good habit to write both of them out, no matter what. Actually, let's talk about this y equation. We know that my wagon is not moving up or down. It is strictly moving side to side. Therefore, we know that the acceleration in that y direction is actually 0 meters per second squared. So if I was to simplify this equation down a little bit, Fn minus mg is equal to the mass times 0, which cancels that whole side out. So I get Fn minus mg equals 0. If I add mg over to the other side, I see that Fn equals mg. So that's a mathematical representation of what we already knew. We knew, and we even proved that we knew, that these two were going to be equal to one another in magnitude based on the free body diagram that we drew. And again, that also was fitting with this equation. But to solve the actual problem itself, all we have to do is plug our numbers into our F equals ma equation in the x direction to solve for friction. I'm going to go ahead and rearrange this equation to begin so that I can solve for FF. So I get negative FF, all I'm doing is adding this FA to the other side, is equal to MAX plus FA. And the reason that I do that is just so that I am able to, I'm going to give myself some more room here, so that I'm able to easily plug numbers in and solve right off the bat for an answer. So negative FF we are solving for is equal to my mass, which is 10, my acceleration is 2, plus FA, which is 30. So now all I need to do to solve for my, I'm going to again erase this just so that I have some more space here. All I need to do is the algebra, so 10 times 2 is 20, plus 30 is 50, so negative FF equals 30, and let's not forget about our units, newtons, and we don't want a negative FF, so we're going to just swing that the negative to the other side. So FF is equal to negative 30 newtons. And there you go. That's how you solve. That's our final answer.